Yep. Hey everyone. Good morning. Let's begin with the third session of the winter workshop for image processing. Uh, so how was the second session? Like you guys had the second session as well with Srinivas, right? So, did you guys have any trouble understanding, or like was it uh, easy to understand?
Yeah, it was fun.
Okay. All right. So I'll begin the recording in Teams as well. And I think now you guys can see my screen, right?
Yeah.
Okay. Okay. So uh, let's start with um, let's start with the third session. So we so today we'll be talking about Huff transform, and then we will be talking about graph traversal. So if those terms are not like they don't sound familiar, then don't worry, we'll be breaking them down one by one. So let's start with Huff transform first. So let's start by discussing a bit of coordinate geometry and uh, revising what we have already, like what we already know from, um, like we already know that equation of a line is y equals to mx plus c, right? So let's say we have a line, something like that. This is the x-axis, this is the y-axis. This is the angle. Usually we refer to it as theta. I'm going to refer to it as alpha right now. We can also uh, write alpha, and when we put x equals to 0, the value of y becomes c. So this intercept is c. So we can also write this as y equals to tan of alpha x plus c, right? So this is just a bit of revision of coordinate geometry. Why we are discussing this is because in this section we are going to learn to find to like segment out or to identify lines in like to identify lines from image. So for example, if this is your image and we have some kind of a polygon in this image, by running the Huff transform algorithm on this image, we can find the equations of these lines of the edges of the polygon. So we can find the equations of those lines. So it's a pretty handy tools. Say for example, if you were to write, uh, let's say if you were, why can't I select it? Yep. So let's say if you were making some kind of an autonomous driving system and you had a camera mounted on top of the vehicle, and the camera were to see the road ahead that lies ahead of the vehicle. So the road would look something like this. So in this case, if you like, a very simple way to find the direction of the road would be to apply the Huff transform on this image, and we then find the equations of the lines of this line and the equation of this line, and then we can calculate where, like we can average out the slopes or like perform some kind of um, calculation to find out where the road is pointing to. So this is um, like some kind of an application for Huff transform. So let's start by discussing what it actually is. What does Huff transform mean? What is Huff transform? So what we basically want to do is we want to find the equations of lines. We can also write the equation of a line in r theta format instead of slope and intercept format. So when we write the equation of line in slope intercept format, we get y equals to mx plus c. But when we write the equation of line in terms of r theta format, we get r equals to x cos theta plus y sine theta, where r and theta are these variables. Let me just draw them really quickly over here. If these are your axes, x and y, and this is your line, then this is your r and this angle is theta. So this is basically polar coordinate, at like the polar coordinate of this point gives us r theta. So in polar coordinates, the equation of a line can be given like this. So I think all of us have studied this form of the equation of line. If we haven't, then it's pretty simple to derive. Like we can probably just do that right now. Like we can derive it from here itself. So let's see, we have this as theta. So this angle would be 90 minus theta, and this angle would be 180 minus 90 minus theta. Oh, some people are waiting in the lobby. Were they able to enter? Right, if someone... Okay, I'll continue. Let's see if they try to join again. So yeah, this angle will be 180 minus 90 plus theta, and this will become 90 plus theta. So right, so this will become y equals, so we can write this as y equals to tan of 90 plus theta plus c, where c is this intercept, which is, so this is 90 minus theta. So this length will be uh, r by cos 90 minus theta, or r by sin theta. Right, I think this is correct. So if you find any calculation mistake, like you can point it out, so we can like get it corrected before. Yeah, so tan 90 plus theta, what is that? I think it is, so over
Minus
here.
cos theta.
Yep. Is
Minus cot theta.
it minus cot theta? Wait. X, and we have plus r upon sine theta. So are you sure it's minus cot theta? Because if that would not compute over here. Oh no, it would. Yeah, that's fine. All right. So this is minus cos theta x, upon sine theta plus r upon sine theta. And if you like rearrange this, you basically get this. So 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 yeah, we basically derived this the polar form of line equation from the slope and intercept form. Great. So why did we derive the polar form in the first place? Like, what do we have to do with the polar form? So we can, like, if we can use the polar form of line equation in a clever way to find the dominant lines in an image. So how do we do that? So let's say that if we keep r and if we keep theta constant, then and if we vary x and y, then we get a line, right? So in this equation, if we keep r and theta constant and x and y are variables, then we plot a line. But let's consider the other case. Let's consider the case wherein we have x and y to be constant and r and theta are variable. What would we like? What kind of a plot would we get in that case? So we want to plot r versus theta. What kind of plot will it be? Let's say we put x equals to x naught and y equals to y naught. What kind of plot will we get?
Sinusoidal of its own face.
Could you repeat? Sinusoidal?
Sinusoidal curve with some face.
Yep. So we'll get a sinusoidal curve. Will yep. So it won't be centered at 0, since we have these extra coefficients with cos and sine. So it will be a little bit offset. It will be something like this. Something like that. So this is 0 and this is 2 pi. So we'll get something of that sort. Right. So why are we bothering with this? Why are we trying to vary r and theta and keep x and y constant? Let's think of it in terms of an image now. Let's think of the image, and let's think of a line inside that image. So if we have this line in this image, we have this pixel, let's say x naught comma y naught, and this pixel x1 comma y1. So for this point, if we fix x naught and if we fix y naught, and if we vary r and theta and plot all the lines that we can plot by varying r and theta, what kind of uh, what kind of a family of lines would we get?
Infinite number of lines passing through that point concurrently.
Yep. So if we vary r and theta and keep x equals x naught and y equals to y naught fixed, we would get a set of all the lines that pass through this point, x naught comma y naught. So we'll get the set of all the lines that pass through that point. So do you find a relation between this set of lines and this graph?
Yeah, the R and theta value of each of those lines when we plot on the, I mean, those are forming that sinusoidal curve.
Correct. So for every theta, we have an r, and this r theta pair represents a line over here that passes through the x0 y0 point. So every r theta pair in this graph represents a line that passes through x0 y0 in this image. So in effect, if we draw this graph, this r theta sinusoidal, then we are representing all the lines passing through x0 y0. Makes sense up till here, right? So uh, let's do that with x1 comma y1 as well. Let's write the equation. Let's write the equation r equals to x1 cos theta plus y1 sin theta. Keep x1 and y1 constant and vary theta from 0 to 2 pi. So what will we get in that case? We will get another sinusoidal, something which would look like this probably. Uh, Something that might look like this. Did I? Oops. Okay. Yeah. Alright. Something that might look like this. So we see that so for all the positive values of r, let's ignore the negative values of r for a moment. For all the positive values of r, these two graphs intersect at this point. So this is the point where the slope of both the lines will be equal. And this is also the point where the distance of that line from origin will be equal. So in effect, you could say that this, like, when two of these graphs intersect, then they represent, like, this point. At this point, they represent the same line, because each point in this r theta space represents a line on the image. So this point represents just one line in this image. So wherever these two graphs intersect, that line will pass through both x0 and y0, since it lies on both the r theta curve of x0 y0 and the r theta curve of x1 y1. That makes sense, right? Is there any question up till now? Okay, so there's no question. So let's move on. So basically, we plotted r theta curves for both x0 y0 and x1 y1, plotting all the possible lines that might pass through those points, and we find that for the positive values of r, that are the only feasible values of r that we consider, we get an intersection at this point. And so this is the point which represents the line that passes through both the points. Let's say we have a third point. Let's say we have a third point called x2 comma y2, and we draw the r theta curve for this point, and we obtain something like this. Yep, something like that. So we can see that this also intersects at the same, like, this also intersects these two curves at the same point, and it represents the same line. So if for all the points on this line we plot the r theta curves, they will intersect at this point, and this point represents this entire line. So what if, for an image what if we have an image of let's say a box. Let's say we have an image of a box, and we perform edge detection on that image. So we basically we obtain what we are basically seeing right now after the edge detection process. And after the edge detection process, we find all the pixels that are non-zero. We find all those pixels, and for each pixel we plot this r theta. We plot this r theta graph for each pixel. So for the first pixel, let's say we'll have this graph. For the second pixel, this graph. Third pixel, this graph. Third non-zero pixel, like for each pixel that is non-zero. For if the pixel value is 0, we don't plot the graph for it. So for each pixel we plot this graph, and then we will obtain. So let's say 500 pixels were illuminated in this edge image. 500 pixels were illuminated. We'll obtain 500 r theta graphs, and we'll plot all those graphs on top of each other. We'll plot all those graphs on top of each other, and we'll find the point which has the maximum number of intersections. So there will be, so let's say there will be 1, 2, 3, 4, 5, 6, 7, 8, 9. There will be 9 points which will have a lot of intersections, where all the sinusoids will line up together. And those points are basically the points which represent the dominant lines in the image. So let's say this point will represent this line, and this point will represent this line. Did you understand why that is the case? Because each graph.
So
yeah, go ahead.
yeah, so in a single graph we get 9 intersection points, or we do that for a set of for a line we take a graph, or for all the lines together we take it.
I didn't really understand your question. So if for each pixel you draw this r theta curve, and then you overlay all the r theta curves on top of each other,
Okay, got it.
and then you count the number of intersections. So the points which corresponds to these lines, they will have a very high number of intersections, and those so this point will have a lot of intersection, this point will have a lot of intersection, and there will be 9 such points, is what I'm saying, corresponding to 9 dominant lines in this image. Right.
Yes, that's clear.
So this is basically how you find the dominant lines, the equation of dominant lines in this image. All right.
What does non-zero pixel mean? Does it specify the intensity of that pixel?
So once we have applied the edge detection on the image, a non-zero pixel is basically any pixel that is not zero. If you want a cleaner result, we can perform some kind of a thresholding, so that we get 0 and 1, clear separation between a zero pixel and non-zero pixel. So yeah, that's
okay.
Right. So this is what the Huff transform algorithm is. Huff line transform algorithm, and this is how you find the dominant lines in an image. So this r theta space, wherein we plot all the lines, all the sinusoidal curves that correspond to the points, non-zero points in the edge image. This r theta space is what we call the Huff space. So we will look at an example now, wherein we will create an image of this Huff space, and like we will visualize how these sinusoids look. All right, so let's move on to the Jupyter notebook. Yep. So let's really quickly, I'll show you the. All right, let's import NumPy as np, import cv2, and import matplotlib dot pyplot as plt. We will also need the math module for this exercise. All right, so we want to define a function that draws in the Huff space. What do we mean by that? We want to define a function that draws in the Huff space. What this basically means is that we want to give it a point x0, y0, y0, and we want to use this point to draw the r theta curve, like for this point basically. So we have to use this equation, r equals to x cos theta plus y sin theta, and draw like this curve for the point x0, y0, which we'll supply in the arguments. So that is what we mean by this function draw in Huff space. Also, we'll need to provide an image onto which we will draw. So this is the Huff image that we have provided. So I think the purpose of this function should be clear. We want to draw the r theta curve onto the Huff image, like onto the image. That is what this function is for a specific x0, y0. All right, so how do we do that? So we can do that by looping through all the, so if we have, and so let me clear the screen a bit and let me draw over here. All right. So if we have this image, and let's say the small grid lines that you see correspond to like the actual pixels in the image. So each of these is a pixel in the image. So how would we draw a graph in this image? We would have to, so basically what I will do is I will count the number of pixels from here to here. I will count the number of pixels. Let's say the number of pixels is n. What I'll do is I'll divide 2 pi into n parts, and each time, and I'll start with 0, and each time I increment a pixel to the right, I will add 2 pi by n to 0. So for the first pixel we have theta equals to 0, and putting theta equals to 0 we find the value of r and plot it. For the second pixel we put theta equals to 0 plus 2 pi by n. So for the second pixel we put theta equals to 0 plus 2 pi by n, and we put that and find the value of r and plot that value. For the third pixel We again add 2 pi by n, and we find the corresponding value of r and we plot that value of r. So it will so ultimately all of these was for visualization only. Ultimately what we'll get is such kind of a curve. So let's go back and let's implement that. So I will iterate over all the columns in the image, half image, and since we are iterating over all the columns, we need to provide like number of columns. So half image dot shape 1 gives us the number of columns, and we'll iterate over all the columns. Now for the for each column, let's say we are in the ith column, so the theta for that column will be 2 pi into column by the size by the number of columns. So if we are in the ith column, we will the value of theta will be 2 pi into I divided by the total number of columns. I hope there is no confusion here. If there is any confusion, please ask. What I basically did was, if the pixels are from 0 to like if you start from 0 and there are n pixels, I map the pixel space 0 to n to the angle space 0 to 2 pi is what I'm basically doing. So yeah, then I calculate the value of r from the equation that we have, x naught into cos theta. We'll have to use maths.cos, and y naught plus y naught into maths.sin theta. Yep. And so we need to remember that we need to only consider the values of r that are positive, since that is the only feasible value of r that we can consider, because it is the distance of the line from the origin. So if r is positive, only then will we draw the half image. So to draw on the half image, like what do we do to draw on the half image? Like we can just access the pixel value and change, like we can just change the pixel value. So we'll have to, like for the ith column, we will like access the pixel value which is at the r height. So in the x direction we have column, and in the y direction we have r, and let's say we plot the value of that to be 255, and let's run this. We have an invalid syntax. Why do we have an invalid syntax? Because I put a bracket over here. Alright, so I hope like this function was fairly easy to understand. Like, if are there any doubts in this function, like how we implemented this function, or what does it do, or any specific part in this function that you didn't understand?
That floor function is only to round off R value to an integer, right?
Yes, correct. So I think we'll have to write and yep, so we'll have to convert this into integer as well. because I don't think like we can pass non-integer values in as array indices. All right. So let's now define a half image. Let's say I want its size to be 375 by 700. So why am I choosing 375 by 700? I chose 700 just because I think like it's a good resolution for theta. So the higher this number, the higher pixels you have in the horizontal axis of the image, the more fine grained you will have your theta to, like the increments will be smaller. You will have a better resolution on theta. So that's yeah. So that's why I keep it 700, and this you could like keep any arbitrary value as long as it is more than the maximum value of r in the sinusoid. So I just selected 375. Let's now just define a d type really quickly to be a d type of, I think is uint8 is the default d type for images. So now we have a completely black image. We can plot that image to see that it's completely black. This is just the function from yesterday that we used to plot gray images. Let's make this maximum value to 55 and let's plot this. So now you can see that it's a completely black image. So let's run the draw in half space function on the half image for a random point. Half image draw in half space, and we provide in our half image, and we provide in a random point. So let's say we provide in a point 180. Let's say we provide that point, and let's see how it works. Oh, okay. So it did draw on the half image, but I haven't added any code to show the image. So let's just copy this code and paste it over here. Alright, so let's run this again, and let's run this again. So yes, I think you can see a sinusoid being drawn over here. The reason this sinusoid is being cut off is because for the values between this point and this point, the r had a negative value, so it went outside the axis. Also, one other thing to note is that this sinusoid is being drawn upside down because in images we have the axes like this. So normally in graph we have the y-axis that goes up. In images we have the x-axis pointing in the same direction, but the y-axis is actually going down. So that is why the graph is flipped upside down. But I don't think like that is a problem. That should not be a problem. All right. So I don't. So there are no doubts up till here, right? We can proceed further, right? All right. So there are no doubts. So let's proceed further. So why don't we why don't we try drawing another point on this half image? So let's say you want to draw this point 50 and 40, and let's run this again. So you can see when we draw 50 and 40, they intersect at this point and at this point. Yep. And Let's try changing it up a bit so we get a better point of intersection. Let's say 2040. And this again, and this again. So yeah, now you can really see the point of intersection of these two graphs. So what our aim is to draw a bunch of these graphs and like find the point which has the most number of intersections. So an easy way to do that, like a common way to do that, is instead of setting the value to exactly 255, we will start out with a blank graph and we will increment the value of the pixel that we are drawing to by 1. So so if a pixel has a lot of intersections and a lot of graphs are being drawn on that pixel, then then we get a very bright pixel in that case. So let's go ahead and let's run this, and let's run this as well, and let's run this as well. All right. So okay, so let's now import an image and let's try to find the dominant lines in that image. So let's import this image, triangle equals cv2 dot time read triangle dot png, and we will import it as a grayscale image. So let's also I would want to clear out the huff image. I want to bring it back to zeros. So yeah, np.zeros like basically copies all the d type and the shape and basically every other aspect other than the data, and sets the data to 0, like sets all the elements to 0, but keeps the size and d type the same. And so if you use that and assign it to huff image, it's basically clearing the huff image and assigning everything to 0. So yep, so we have imported a triangle. Let's now view what this triangle image is. Also, by the way, if you're wondering why there are gaps in this graph, like over here and over here, it's just an artifact of like rendering this graph by like PLT doesn't like matplotlib pyplot doesn't do a very good job of rendering this graph. So if you render this in Opencv using cv2.imshow, like you will see like that the graphs are like continuous, they are complete. So that's not something that we should worry about. All right, so let's view the triangle image. What does it look like? I think there's some. Oh, okay. So maybe I don't have this triangle image in my folder. Let me quickly go to the folder. We have the triangle image, and I also want to copy this image. Alright, there. So now this should run. Yep. So this is the triangle image that I was talking about. This image, now we will try finding the equations of the lines of the, or at least we'll try plotting them in the huff space. We'll try plotting all the r theta curves from the non-zero points in this edge image, and we will see that since we have 3 dominant lines, it's a triangle, will have 3 intersection points in the half image. So let's do that now. So we want to iterate over all the pixels of this image, and we want to find out which pixels are 0 and which pixels are non-zero. So we will iterate over all the pixels we'll iterate over all the rows of this image. Shape 0, yep. And we will iterate over all the columns of this image. And if this image has a non-zero value at the pixel that we are considering, then we need to draw in half space using that particular point. So we'll supply in the half image, and we'll supply in X, and we'll supply in Y, and that's it. That's basically it. So we are iterating over all the pixels. We are finding out which pixels are non-zero, and for the non-zero pixels we are drawing in the half space. So we can copy and paste this code again, and we can view the half image. Yep. So let's see what this does. So this is the half image. I don't think like you can see the points very nicely since they are not very bright, but let's try reducing the Vmax a bit so you can see it a bit more clearly. Let's run this again, and let's run this again. So now you can see a bit more clearly 3 intersection points that I was talking about. If we reduce the Vmax even further, say we bring it down to 50, so okay, let's bring it out even more. Let's bring it down to 30. There we go. Now you can like very clearly see the points that I was talking about. So this pattern that you see is drawn due to multiple sinusoidal waves overlapping on top of each other, and wherever we have the brightest point, those are the points of intersection. I hope this makes sense, because like, so we have 3 points of intersections and we have 3 dominant lines in this image. So once we know the coordinates of this point of intersections, we know the r and theta for that point. So once we know the r and theta for that point, we can like back calculate the equation of the line. Is there any question up till now? Okay, so this is somewhat of a slightly complex concept. So if you have any questions, then you should definitely ask, because like it might like for me personally, it took me a while to get it when I was first studying about it. So if you have any questions, then like go ahead and ask. If not, then like we can continue.
While calling the function draw in half space, so it should be y comma x, right? Since
Over here?
yeah.
No, because we defined it that way, right? We had x naught comma y naught, and then we also use the formula with x naught correctly and formula with y naught correctly. So
But while initiating the loop, y values correspond to the
over here,
I mean for y in range triangle dot shape 0.
oh, so since all images are stored as matrices, so the first so in the shape the first value corresponds to the number of rows. So in fact, over here we are traversing the number of rows, like we should be traversing. So y is traversing the number of, so over in this image, y is traversing the number of rows, and x is traversing like all the columns.
Okay.
Yeah.
I confused. I was confused.
Yeah. And over here we are writing it in the form of y comma x instead of x comma y, because like generally we index matrices using row comma columns convention. So that is why, because like numpy follows the no rows comma column convention. So that is why we are using this to index in this way. All right, so that was half line transform actually. I should add a cell above, and this is half transform, and we are talking about half line transform. All right, so this is basically how you draw in the half space. Let's look at the Opencv function that lets us draw in the. So the Opencv function basically draws in the half space, and it basically only provides us with the, like, its output gives us the brightest intersection points. So its output gives us the r theta values, and then we can use them to calculate the equations of the lines. So let's quickly go to Opencv documentation, just so I can show you Opencv documentation half lines. All right, let's see what they have to say. Yes. So
Hello.
hello.
I had a doubt. How are we going to extract the pixel information? I mean, the pixel which is the brightest. If there are multiple such pixels, then the intensity of each pixel will be different, and we can't
Right.
just use the maximum function to extract the information of that pixel. So how are we going to do that?
Right. So till now I was saying brightest, but what I should really have been saying, like what I should really have said was, we are basically going to threshold this image, and for the points that come over the threshold, like for the points that surpass the threshold, those points will correspond. So the lines that corresponds to those points will use those lines as the dominant lines for this image.
But we can't use general threshold for this, right? Because if we use some general threshold, then some of the points which are closer to the actual point will also get included, right?
Right, but that is a problem with the Opencv function as well. So that problem still exists. So you can use some kind of a neighbor separation, maximum suppression technique. You can look at like maximal suppression techniques on your own if you want to kind of suppress the non-maximal points.
Okay, so we'll have to find neighborhood maximum, something like that.
Yep. But as you will see in the Opencv function of half lines, what you will get is, like, you will get a dominant line like that, and you will get another dominant line which is very similar to that line, and another dominant line which is very similar to that line. So it is, and it depends very heavily on the threshold that we set. So so that's still a problem with this method, but like even so, like even after that problem, it gives like very good results. So uh, so yeah, this is the Hufflines documentation. If we open up this function, we can see that uh, so they basically tell us how to use this function. I'll just show you an example of how we can use this function. Right, so use this function in such a manner. CV2 Hufflines triangle. So we first provide the name of the image that we want to find the dominant lines on. Then we alright over here. So and then we give it the row. The uh, row is actually how like what the increment should be for the radius. Uh, so right now we have the increment of 1 for the radius, but we can also have an increment of 0.5 for the radius. In that case, this half image will be of a y height of like twice of 375. So right now it is of 375. If we consider like increment in radius of 0.5, so to accommodate the same range of radius, we'll have to double this height. You understand what I'm saying, right? So each pixel accommodates um, a space of one radius, like a space of one radius. So if you want to accommodate a space of 2 radius in 1 pixel, we'll have to half this value. We'll have to half the y dimension of the half image. So that's basically the value of row that we are specifying as the second argument over here. Then we have theta as the third argument. That's the same thing as row but in the x direction. So I specified 700, right? I specified 700. If I wanted the right, so if I want to keep 700 over here as well, then I will have to specify 2 into np dot pi 2 pi upon 700. So this is basically what I will have to specify if I want to keep uh, the x-axis to be 700 pixels long. So if I want to keep the x-axis to be 180 pixels, then I'll specify this. In pi by 1/8. So if I want to keep the x-axis to be 360 pixels, I'll specify this. If I want to keep it 180 pixels, I'll specify this. So something like that. Then we have the threshold, like the value of the threshold that we'll use to find the points which correspond to the dominant lines. And then we have a few extra parameters that you don't really need to worry about them. These are these parameters: SRN, STN, min theta, max theta. You can read about these parameters over here, but for like this exercise, you don't need to worry about those parameters. So yeah, so let's execute this and let's see what we get. So currently all the lines are stored in the lines array, and if we print it, we see that we get more than 3 lines, right? So uh, we get more than, so this is r and this is theta, so we get r theta pairs as an output of lines, and we see that we get more than 3 lines. So definitely it's not uh, giving us like the exact only 3 lines, but it also has some repetition. So maybe there are 2 lines over here, 2 lines over here, and 1 line over here, something like that, right? So and if we decrease this threshold, let's say we make it 40 and then run it, we'll probably, so we'll get even more lines. If we make it 10, we get even more lines. We get a lot of lines in this case actually. So yeah, this shortcoming is present in even in the Opencv implemented function. All right, so we have the lines array. Now how, like, we want to use the lines array to display the lines. uh, so first we would want to make a lines image, mp.zeros underscore like triangle. What this basically does is it creates a copy of the triangle image into the lines image, but it sets all the values to 0, so it's blank. Now this piece of code for displaying the lines, I just grabbed it from the Opencv tutorial, and so this piece of, so what this code basically does is that it, from the lines array, it reads all the lines and it displays it on the lines image. And then all we need to do is display the line image on our Jupyter notebook. All right, so as you can see, we get the lines image, and if you look closely, we see there are 2 lines in this side, and there are 2 lines in this side, and there are 2 lines in this side. So we see that I get like Huff's lines does not give like very, it does not perform a non-maximal suppression while doing thresholding. So yeah, that basically is Huff's line transform. So are there any doubts up till now, like as to how we got this result?
Yeah, I mean, in this lines equal to cv2.offlines function,
Mm-hmm.
the thresholding is the normal one, or I mean, can we use inverse thresholding in this case directly from the function?
I don't think you can use inverse thresholding. Also, why would you want to use inverse thresholding?
For suppose the image you have has a black background and then image is of white color. So if the case is reversed,
Okay.
then instead of changing the image, inverting the colors,
Right.
I mean, is there
But
any way of
right. But we
doing
have,
it
but
directly
over
from?
here we are drawing the Huff image ourselves, right? When we use the Huff's lines algorithm, uh, the OpenCV draws the Huff image itself. It doesn't use our Huff image. This is just for demonstration purpose. It is not being used over here. So it draws its own Huff image. So in that case, you don't need to worry about um, like how the Huff image looks. You just need to worry about the threshold.
Yeah, my doubt is that in this case the threshold is 50.
Mm-hmm.
So for all the pixels whose value is greater than 50 will be considered while drawing the graph and for its analysis behind, which is not known the algorithm.
Right.
What if I such that the points which are less than 50? So, as in case of inverse thresholding.
So all the points which are less, so I'm still not sure why you would want to think about all the points that are less than 50. So if we remove these 3 points and we consider all the points that are less than like the value of these 3 points, then we are basically getting a lot of lines, right? And like, why would we want a lot of gibberish lines?
Okay, that the thresholding is to identify the points on the intersection points, right?
Yep.
Okay, I thought that was to read from the initial triangle image.
Oh no, so thresholding is for the Huff image. All right. So any other questions for from Huff's line transform? Okay, so if there are no questions, then let's move forward with Huff circle transform. So for Huff circle transform, we will not be trying to implement this algorithm ourselves like we tried to implement the Huff line transform and the Huff image for that Huff line transform. But we'll still be discussing the algorithm, and we'll be using the Opencv function to find some circles. So let's discuss about Huff circle transform. All right. So let's go back to the whiteboard and sorry. So let's say this is our image and we have a line. To define any line, what is the maximum number of parameters that you need? Like, can someone tell like the maximum number of parameters that you need to define any line?
A point and a slope. Two.
Yep, 2. So either a point and a slope, uh,
Or 2 points.
or yeah, or two points. So even 2 points is more information. So giving 2 points is basically saying 4 values: x0, x1, y1, x2, y2. Even that is more information. Even a point and a direction is more information. Like, all we need to give is, let's say, a slope and its distance from the origin, or a slope and its y-intercept. So things like that. So only two parameters are required for a line. And by parameters, I mean like only two numbers are required for defining a line.
Actually, when we say y-intercept, it is inbuilt that the x-intercept is 0. So that's also given, right? Sorry, x-intercept, not x-intercept, the x value for that point.
Right. So yeah. So when you say y-intercept, the x value of that point is given. Okay. Um,
So that's also a given.
Fair, but mm, I guess you could say that. Yeah. Uh, but so I'm so yeah. Let's look at it from the perspective of defining an equation. So if you want to define an equation for a line, how many independent parameters are there? Let's think of it in that.
That's true. That's true. Okay, sorry.
So yeah.
My bad.
So in that case, we have two parameters for a line. Right. What was I? Yeah. So we only need two independent parameters to define a line. So what about circles? How many parameters do we need to define a circle?
Three.
The coordinates of the center and radius.
Yep.
X naught, y naught, and
So we need three parameters to define a circle. For a circle, which are the coordinates of its center and radius. So you could imagine that to define a half space of a line, we need r. So for the half space of a line, we had r theta, and we could draw all possible lines in that half space. So in that half space, each point would correspond to a line in the image. So you could say that the half space of lines is 2D, but the half space of circles, as you can probably guess, would be 3D. So since we have three parameters over here, so we'll have three dimensions to consider if we try to visualize the half space of circles. So since we already are a bit familiar with half spaces now, I will go ahead and I'll try to explain the half circles algorithm right away. So let me clear this up. All right. Let me center this somewhat over here. All right. So let's say we have this three-dimensional half space of this image, three-dimensional half circle space of this image. So what would this half space look like? How would you construct the half space of this image?
we fix any point on the circle.
Alright, we fix any point on the circle.
And we vary x naught, y naught, and r.
We vary. Sorry, could you repeat?
Yeah, we fix a point on the circle that represents x comma y.
Okay.
And we vary x naught comma y naught and r.
Yep, we vary x naught comma y naught and we vary r. So what would that give us? So let's say we fix x comma y and we begin with r equals to 0. So in that case, x naught comma y naught will be equal to x comma y. So we'll have the same point. Let's take r to be 1. So if r is 1, let's say it is 0.1. So if r is 0.1, I will increase r in small increments and we'll see how the half space looks. So if the r is 0.1, then how many possible centers could there be such that x comma y lies on the circumference of a circle from that point, like from that point as a center? How many such centers could there be? There could be.
There will be infinite.
Yep, there could be infinite centers, and the locus of those centers would be a circle of 0.1 radius around xy, right?
Yeah.
Yep. So the locus of x naught y naught will be a circle of 0.1 radius around xy. So if r equals to 0.2, the locus of the possible circle centers would be a circle of 0.2 radius around xy. And similarly, if r equals to 0.3, we'll have a locus of 0.3 radius that represents all the possible centers around xy. So for a single point, the half space. So for a single point x, so this is the x-axis. Let's say this is the x-axis, this is the y-axis, this is the r-axis. For a single point x comma y, or x0 comma y, or let's say x1 comma y1. For a single point x1 comma y1, the half space would look like a cone. So if this image had a single point, let's consider this image. This image has a single point, a single pixel bright. So the half space of this pixel of this image would be a single, like a cone, with the apex of the cone lying at r equals to 0, x1, y1, 0, 0. This would be the apex of the cone, and like it would keep on increasing, and this would like go on up till infinity. So that would be the half space of this of a single point on an image, of a single pixel on the image, right? So, and just to like help you visualize, this cone is not completely filled. This is just the surface of the cone that will be in the half space. So only the surface of the cone is included, like it will be the so you understand my point, right? Like this cone is not filled. All right.
Yeah.
All right. So if so it can be a little bit hard to visualize for multiple points. Let's say if we have 2 points, then understandably we can have like multiple circles that can pass through those 2 points, right? We can probably have a circle like this, a circle like this, a circle like this, and that gets reflected if we draw if we draw 2 cones next to each other. Then those 2 cones intersect at infinite points, and those infinite points represent the circles that we can draw through those 2 points on the image. And if we draw let's say we draw, so if we have 3 points, then we have a single circle that passes through all the 3 points. And like if you plot 3 cones, like you will see that they intersect at only 1 point. So that is basically how half circle transform works. If you have a lot of points, then it can be very hard to visualize the half circle transform. So that is why like we will not try to implement it. But a good exercise for like a good homework exercise might be to implement the half circle transform and play it as an animation such that the first frame plays the xy plane of the half circle transform. The first frame plays the xy plane of the half circle transform at r equals to 0. The second frame plays the half circle transform at r equals to 0.1. Third frame plays at r equals to 0.2. and so on. So you could try to make a video animation out of it, and that would be a very good visualization of how the Huff transform looks in 3 dimensions. So is there any doubt up till this point? All right. So I do understand that this is slightly more complex than the Huff's line transform, but if you do have any doubt, then you can ask. But if you don't have any doubt, then great, then we can proceed. So let's move on to some examples of Huff circle transform. Uh, so let's bring in the circles image into our Jupyter notebook. And we'll bring it as a grayscale image, and we'll display this image. Right. Circles. Oh, my bad. Okay, we have circles.png. Right. So we have this image. Shall we take a 5-minute break? Oh, we can, like, this section is almost over, so we can take a 5-minute break after that. That works, right?
Yeah, sure.
Okay. So we have this image that we loaded into Jupyter Notebook. Let's now run the Huff circles Opencv function. So the Huff circle Opencv function looks something like this. We have the input image that we want to find the dominant circles in. We have the method to find the circles. We have Huff gradient and we have Huff gradient inverse. If you want to read about it, then you can go ahead and look at the documentation. They are pretty thorough with it. In fact, let's look at the documentation right now. Circle transform. Yep. So we have Huff circles. We have the first argument as the image. The second argument is the method. The third argument is dp. Now what is dp? dp is the inverse ratio of the accumulator resolution to the image resolution. So for example, if dp equals to 1, the accumulator has the same resolution as the input image. So we have put in dp equals to 1. So our Huff space, our Huff image that OpenCV will create, it will have the same resolution as the input image. Okay. So minimum distance between the centers of. So the next argument is min_dist, which gives us like the minimum distance we want between centers of the circles. If we specify it to a very small value, then like we can have multiple circles bunched up together, which we like might not want. So this is some kind of a non-maximal suppression. So we have min_dist, like I set that to 15. We have param1 and param2. So these parameters, like you will have to tune these parameters to get the results you want. So these parameters don't usually. So in fact, the default parameters that they have given, they did not even give any result in this image. So I had to tweak them to get some results in this image. Then we have min radius and max radius. So that just means like what allow. So the bounds of the possible radiuses of the circle. So that's that. So if we yep, so if we run this, and then I just quickly grabbed this code to display the circles from Opencv tutorials. What I basically did is I created a blank image which is like the same shape and size as the circles image. It's just black, and to that black image I'm drawing the circles detected from the half circles. So the half circle detects the circle and stores it in the circles array, and I'm reading, and then we read the circles array and use the center and radius information to draw circles on the detected circles image. So now we need to draw the detected circles image, so that we can do just by doing this. So you can see the circles that we have detected. We first draw the center of the circle, so that is why you see the dots in the center, and then we draw the outline. So that's how you see the outline of the circle. So that is how basically half circle transform works. And so you can so this is a very idealistic case for half circle transform. Like you can use it on everyday circular objects like uh, discs and like balls to so and you don't even need to run an edge detection algorithm before running half circle transform. So that's a plus point of this. So yep, the so before we take a break, there's this one more topic I wanted to discuss about, and that is something that we should have touched up in Half-line. So Opencv gives us two functions for Half-line. The first is Half-lines and the second is Half-lines P. What we discussed about was Half-lines, and we have the second function called the probabilistic Half-line transform, and it uses some kind of a random sampling algorithm as far as I know, and it directly gives you, so instead of outputting r theta, it gives you the it gives you 0.1 and 0.2 for the dominant line. So let's say we were talking about the triangle image, it would give you the coordinate of this point and the coordinate of this point. It would return those, and then you could use those points to draw a line segment between, or you could use those points to find a line equation. Or so the output format of Half-lines P is much more convenient if you look at it that way. So yep, that's all I had to discuss about. If you guys have any questions right now, we can take up questions and then we can go for a 5-minute break.
Excuse me.
Yep.
So for the link you shared yesterday, it's showing that I don't have access.
Oh, okay. So, alright, so let's just pause the recording. Let's continue with what we were discussing. We were about to start a new section. So, let's start with graph traversal. And in graph traversal, alright, so yeah, let's start with graph traversal. So let's discuss about graphs. What are graphs? Okay, so can someone tell me what graphs are?
So a graph is basically like an ordered pair of vertices images, commonly denoted by VNE.
Right. So a graph is basically a. So what he said was like, okay, someone wrote something in the chat. Okay. Give me 1 second. Oh, right. So there are two kinds of graphs. So one is visual representation of data. The other one is that the other one is the one that we'll be discussing today. The other one is a collection of ordered pair of vertices, and so to give some intuition to you on what graphs are, we can think of vertices as nodes, and we can think of edges as the bridges which connect those nodes, or you could think of those as islands, and we can think of edges as bridges that connect the islands. So this kind of a structure is what we call as a graph. So this is, let's number the nodes, or let's number the vertices. So these are called the vertices of the graph, and these are called the edges of the graph. So uh, so graphs can be of like multiple types. Some graphs are directed. So in directed graphs, the edges that you have, they have a specific direction assigned to them. So each edge has a specific direction assigned to it. So when does the direction of an edge become of importance? So let's say you were traversing a graph. So you could traverse the graph. So let's say if you think of it in terms of an island and bridge analogy, these bridges are one ways, and traffic can only flow through these bridges in this direction. You could think of it like that. So if a vehicle has to go from 0 island to 2 island, it will have to go from 0 to 1 to 3 to 2. It can't go from 0 to 1 to 2. You could think of it like that. So those are directed graphs. Then we have undirected graphs. So undirected graphs are graphs in which the edges don't have um, directions assigned to them. So in that case, a vehicle that's starting from 0 can go to 2 by either going from 0 1 2, or it can go from 0 1 3 2, or it could go from 0 1 3 1 2, or 0 1 3 1 0 1 2. So those are undirected graphs where the edges don't have any direction assigned to them. All right, so so there are more, like, many kinds of graphs, like, but let's not talk about those right now. Let's talk about uh, how we can find the connected components of a graph. Let's break down that sentence one by one. So sometimes, so a graph doesn't need to be all connected together. What do I mean by that? let's say let's draw a graph. The red dots are vertices of the graph, and the green lines are the edges between the vertices. So let's draw this graph, and this whole thing is one graph. It contains, so a graph can have uh, like separate islands inside it. So this is an entirely connected component, and this is an entirely connected component, but those two don't have any edges connecting them together. But we consider it as one graph. So this graph by definition has these two uh, these two islands inside it. So how do we find all the vertices connected to, let's say, this specific vertex? We want to make an algorithm to find all the vertices connected to this specific vertex. If we number the vertices 1 0 1 2 3 1 4 5 6, and we want to find the vertices connected to 0, that is to say, uh, if we start from 0, what vertices can we reach to by traveling along the edges? Then we will get the answer as 1 2 and 3. The vertices 4 5 and 6 are not connected to 0. Similarly, 4 5 and 6 are not connected to 1. 4 5 and 6 are not connected to 2. So we want to find an algorithm that when we give the algorithm an input of a vertex, it finds all the vertices that can be reached from that vertex. So how do we go about doing that? So we can do that by using the breadth first search algorithm. Let's look at the breadth first search algorithm now. So let's all right, let's create a graph. Let's create a graph and number the vertices. And draw edges between the vertices. Let's say something like that. Let's say we have a connection over here too. So, and we want to use breadth first search. How do we find all the so by looking at it, we know all the vertices in this graph can be reached from 0. But to explain you the working of breadth first search, I have used this graph, and we'll now look at how breadth first search actually works. So breadth first search, we need to initialize it with an input vertex. So it will be the vertex where we will start from. So let's say we consider 0 to be our input vertex. This is the vertex which we start from, and we want to find all the vertices that are connected to this vertex. All right, so we have so what we basically do is from 0 we look at all the vertices that are directly connected to 0. So we have So what are the vertices that are directly connected to 0? We have 1, we have 2, and we have 3. Only 3 vertices are directly connected to 0. So great. So now we know which vertices are connected to 0. We start visiting those one by one. So let's visit 1. Now we repeat the entire procedure again. We ask the question which vertices are connected to 1. We see that 0 and 2 are connected, but we already visited 0 and we already have 2 to visit. So we'll just proceed. So now we have 2 so now we visit 2. When we visit 2, we have how many vertices are adjacent to 2? We ask this question. We get 0, 1, 3, and 5. 4 vertices are adjacent to 2. But 3 is already waiting to be visited. So we just add 5 to the waiting list. Now we visit 3. And so how many vertices are adjacent to 3? We have 0, 2, and 4. 3 vertices are adjacent to 3. But these two already have been visited, so we just add 4 to the waiting list. Now, since 5 was added to the waiting list first, we'll go there and we'll ask how many vertices are to be visited, are adjacent to 5, and we see that only one vertex is adjacent to 5 and it has already been visited. So we'll just move on to the next waiting vertex. So now 4 is waiting. So we will come over to 4 and we'll ask the question how many vertices are adjacent to 4. We see that 3 is adjacent to 4, but it has already been visited. So we'll just terminate the entire process here since we run out of waiting vertices which are in the waiting list. So and now we just count all the vertices that we have visited. So in this way we can find like all the vertices that are connected to the initial vertex that we start with. So this is essentially what breadth first search is. Is there any doubt up till now? In the explanation of breadth first search, is there any doubt? Or in the explanation of graphs?
So what will be the application of these nodes and the bridges?
What will be the application of the nodes and like vertices and edges?
About these graphs?
I'm not sure. I don't understand your question. Could you repeat?
What will be the applications of these graphs and finding the
Okay.
limits?
Right. All right. Okay, so let's discuss that. What will be the application of it? Let's discuss that. All right. So let's say that you have an image and you have a shape over here. Like you have a contour over here. Like you drew something, and now you want to fill this entire region with a certain color, just like in paint.
The fill tool.
The fill tool, exactly. So if you take this pencil and if you draw something and you take the fill tool and you click in the middle, it automatically fills the entire covered region with that color, right? So how does it do that? How does it know like where to stop filling and like what region is the boundary region? How does it know that? So it performs the breadth first search to find all the components, like find all the vertices connected to the initial vertex. So in this case, in the case of an image, we treat pixels as vertices. So each of this each of these pixels are vertices, and each pixel is connected to the vertex to its right, to the pixel to its bottom, to the pixel to its top, and the pixel to its left. So each vertex has 4 edges assigned to it. Each pixel has 4 edges assigned to it. So you could think of all images as graphs of this format. And yep, and when you draw with a pencil, when you change the color of a pixel, you are essentially breaking the edge of that pixel with the neighboring pixels. So once you have a broken edge, let's say like that, and then you initiate a fill tool right over here, then it will only fill this region and not spread to that region. You get my point?
Yeah, got it.
Right. So basically you can use fill tool to fill regions. The other use of breadth first search is that it's that if you have like you could use it to solve, if you have a maze and you have a start point and an end point, and there is a path from the start point to the end point, you can use the breadth first search to solve that maze basically. So this goes into somewhat of a path planning thing, but yeah, that's beyond the scope of image processing right now. So for image processing, you could use breadth first search to find, let's say there is a white blob, and you want to find the area of that blob. So you want to know how many pixels are inside that blob. So you start scanning the pixels, and so one thing you could do is like you could iterate through all the pixels and find all the white pixels and find the area of the blob. But that is inefficient because in that case you'll have to traverse through all the pixels of the image. So the other thing you could do is take just one pixel of this blob and start a breadth first search, and that breadth first search will give you all the pixels connected with that uh, initial pixel, and then you can just sum the number of pixels and get the area of that blob. So this is some, like, in this way breadth first search could be useful. Right. So now that we have discussed the applications of breadth first search, let's look at how we can implement it. So to implement a breadth first search, we use, so I was referring to the waiting list that is actually implemented as a queue. So if you don't know what a queue is, it basically is an array where things that are added first are the things that are deleted first. So just like in a queue of people who arrive first are the ones who get to get to the front and then get out of the queue first. So similarly, things that are added to the queue first. So let's say I have these numbers 0, 1, 3, 4. I add 0 over here, 1 over here, 3 over here, 4 over here. And then when I start deleting numbers, I'll be deleting from this end. So 0 will be the first to go, then 1, then 3, then 4, in the order of their arrival. So the key with breadth first search is that we have to first explore all the neighbors of of the current element, and only then we can move forward with exploring those neighbors, with the exploring the neighbors of those neighbors. So in breadth first search we'll have to explore, so you get my point, right? We have to explore all the neighbors. So let's say for 0 we had to explore 1, 2 and 3, all 3, before we could move on to exploring the neighbors of 1, which in this case was just 2. But in the case of 2 there was 5, but then we couldn't jump to exploring the neighbors of 5. We have to first explore the neighbors of 3, and if the neighbors in the neighbors of 3 we find 4, only after that we can start exploring the neighbors of 5. So uh, I hope you get my point. So we use a queue in order to uh, like implement the waiting list that I had been talking about. So let's say we have the queue, and let's start the BFS search once again. Let's start the BFS search once again. So we have 0 as our initial element. Sorry, we have 0 as our first element. So if we add that to the queue, we add that to the waiting list. Now we explore all the um, neighbors of 0. So the first neighbor of 0 is 1. We add that to the element, to the queue. The second neighbor is 2. We add that to the queue. Third neighbor is 3. We add that to the queue. Alright. So now we have explored all the neighbors of 0. So we mark 0 as visited. We have already visited it since we have explored all the neighbors. Now we visit 1, and we explore all the neighbors of 1. We see that, so why do we visit 1? Because it's the next in line waiting to be explored. So since 1 is next in line, we explore 1, and we see that it has only 2 as the neighbor. So now we have visited 1 as well. So now we go to 2. We see that it has 3, and it has 5, and it has 0, and it has 1. But 0 and 1 are already visited, and 3 is already in the waiting list. So we just add 5, and we cancel out 2 because we have already visited it now. Now we go to 3 because it's next in the waiting line. So in 3 we have only 4 as neighbor, the rest are visited, and and the rest are visited. So we add 4 to the queue, and once we add 4 to the queue, we've already visited 3. Next in line is 5. So we go to 5. We see that 5 has only one neighbor, 2, and it has already visited. So we can't do anything over here. We move on to the next one. So next one is 4. We see that it has only one neighbor, 3, and it is already visited. We can't do anything here as well. So we cross this out. We mark this as visited, and thus we come to the completion of this breadth first search. And all the vertices that we visited here are the members of the connected component. So this is how we implement breadth first search. Any questions with this? Alright, so if there are no questions, then let's move on to implementing it in code. So let's just let me familiarize you guys with the idea of an adjacency list. What is an adjacency list? So an adjacency list is basically, it is a list of, let's say a graph has so for this graph we have 0, we have 6 vertices. So we have 0, 1, 2, 3, 4, 5, let's go down here, 5, 6. All right. So we have 6 vertices in this graph, and for 0 we have 1, 2 and 3 as neighbor. So we'll write 1, 2 and 3 over here. For 1 we have 0 and 2 as neighbors. So we'll write 0 and 2 over here. For 2 we have 1, 0, 1, 3 and 5. Let's write that over here. For 3 we have 0, 2 and 4. 0, 2 and 4. For 4, oh, we don't have a 6th one. For 4 we have only 3. For 5 we have only 2. So this right here is what you call an adjacency list. It is a list of all the adjacent vertices for every vertex in the graph. So this list actually contains the entire information for, like, if you just read this list, then you can you can make this graph, you can reconstruct this graph. So this list contains the entire information of that graph. So this is what we'll be using for as the input, like this is how we'll be storing that graph in our code. So let's say our graph has 9 vertices, and we will also make an adjacency list for the graph. So you can see that adjacency list is a list of lists, right? So let's initialize the adjacency list with 9 empty lists. It is a list of lists. So now we initialized it with 9 empty lists. Let's run this. You can see that we initialize the adjacency list with 9 empty lists. And okay, so let's now define a function to fill up the adjacency list. So let's now define a function add edge. What does add edge do? It takes 2 inputs, v1 and v2, and it adds an edge between them. How does it add an edge? So by adding an edge, we mean that in the adjacency list of v1, it will add v2, and in the adjacency list of v2, it will add v1. So that is what we mean by adding an edge. So this function basically builds up the graph. Alright, so we have this function in place. So is there any doubt for this function? Alright, so if there is no doubt, then let's proceed for okay, so let's now construct our graph. So I'm going to construct a graph which looks something like this. Let's copy this over here and let's visualize this graph. Alright, so let's visualize this graph. We have 0, we have 0, and that is connected to 1, and that is connected to 0 is also connected to 2, and 1 is connected to 3, right? And 2 is connected to 3, and 2 is connected to 4. So we have 4 over here, and 4 is connected to 5, 4 is connected to 5, and yep. Then we have 6. 6 is connected to 7. 7 is connected to 8, and 8 is connected to 6. So this is the graph that we have at hand. Now we want to write a function called Dfss, which will take an input of a seed, and it will output the connected components, like all the vertices that are directly accessible from that seed. That is what we want to do with Dfss. So okay, so let's start with the implementation. So first of all, we will want to create the queue. So yeah, there we have created the queue. So but this queue is empty. We need to like initialize it with some value. So we'll initialize it with the value. We'll put in the value of the seed that we get, because it is the first vertex that is waiting to be explored. We'll also create a visited array that will be false initially, since none of the vertices are initially visited. And since we are going to visit the seed vertex in the very beginning, we'll set it to true. So since we are going to visit the seed vertex in the very beginning, we'll set the visited of the seed vertex to be true. And then we will have the CC array, the CC list, which basically will store the connected components of the the vertices connected directly accessible from the seed. So what we want to do while implementing Dfss is we want to keep doing what we are doing until the waiting list has no entries left. So if the waiting list has entries left, we'll keep iterating. Otherwise, we'll stop iterating. What will we do each iteration? So each iteration, we will get the first element of the waiting list. So in this way, we get the first element of the waiting list, and then we will remove the first element from the waiting list. So now the waiting list has the next element as its first element. Now what we want to do is so the element that we recently popped from the queue, from the waiting list, we want to iterate through all the adjacent vertices of that current element that we popped. So for adjacent in the adjacency list, so for all the adjacent vertices in the adjacency list of the current element, we want, so if the adjacent vertex has already been visited, so let's say um, wait, over here, yeah. So when we start with 0, let's so when we come to 1, let's say we have 2 as the neighbor, but since 2 was already added to the queue, it has already been marked off as visited. So we will not again add two to the queue. So that is why we have this check as if not visited. um, if adjacent vertex is not visited, then we want to add it to the queue, we want to add it to the waiting list, and we also want to add it, and we also want to mark it as visited, so that no one else adds it again to the queue. So once that happens, we can then go ahead and add the current element to the connected component and then return the connected component. So that's it. That's like pretty small code for BFS, and we can use this code to like access how many vertices are directly, like find out how many vertices are directly accessible from any given vertex. So let's try that out. Let's see using our visualization that we just made. Let's see. Yep. I hope the graph is visible. So using this visualization, if I initialize the seed to 0, what do you think the output will be? Like how many vertices will be there in the connected component?
All vertices.
Sorry, did you say all vertices?
Yes.
No, all vertices won't be there because
Except 1 to 5.
yep. So 1 to 5, 0 to 5, all vertices will be there in the connected component. So we'll have BFS of 0. Let's run that, and we have 0, 1, 2, 3, 4, 5. We have all the sorry. We have all the from 0 to 5 in the connected component, but we don't have 6, 7, and 8. If we give 2 as the seed vertex, then also we should see 0 to 5, right? And that is exactly what we see. So the order has changed because we start with 2, but we see that 0 to 5 all are there. If we start with 6, then we should not see 0 to 5, we should see 6, 7, and 8, and that is what we see. If we start with 8, we get 8, 7, and 6. So you can see that our BFS algorithm is working. All right. So any questions up till now?
Could you explain this, the BFS, the logic of the code once again? Like how it is like executing what we are thinking right here.
All right. I'll use this. I'll use this to explain. Sorry. So first we have q equals to seed. What do we want? So when we start the BFS search, we select a initial vertex that we want to search from. So our waiting list or our queue will have that initial vertex inserted at the first position. So that is what we have done here. Then we want to have a visited array. We want this array because uh, whenever we insert an element and then whenever we insert an element into the waiting list and then we visit that element, we don't want to insert the elements or we don't want to visit the elements that have already been visited, right? So let's say we are at, so let's say we visit 0 and then we visit 1, then we visit 3, then we visit 2, or we visit 0, then we visit 1, then we visit 2, then we visit 3. Once we visit 3, we'll have no option to visit any other visit any neighbors of 3, because the neighbors of 3 are 2 and 1, and those will already have been, those, by the time we visit 3, those will have been visited. So to keep a track of which vertices are visited and which are not visited, we have this visited array. So yeah, so then we initialize, the visited array with all false values since none of them are visited. Only the value for seed, that is the initial vertex, we change it to visited since we are like visiting it the first. Then what we want to do is we want to iterate and search through the graph until the waiting list remains non-empty. So if there is even a single element in the waiting list, then we want to keep iterating. So once we enter the loop, what we do is we pop out the first element. So this first element gets it gets popped out from the queue, and it gets stored into cur. And now we visit all the adjacent vertices of the cur. So all the adjacent vertices of cur are 2 and 1. So since both have not been visited yet, we add them to the waiting list. So we add them to the waiting list. Add it like this, right? We already have 0 marked as visited. Now we add 1 and 2 to the waiting list, and we also mark them as visited. So now when we take out 1, because it's the next in the waiting list, now when we pop out 1, let's pop out 1. Now when we pop out 1, we see that only 3 is the neighbor that is not visited. 0 is already visited, so we will not pop 0 back into the queue. So that is why we have this visited array. So alright, let's back up a bit. We had 1 over here, and we marked 2 and 1 visited, and we added 0 to the connected component list. We added 0 to the connected component list. So this is our final result output, and we added 0 to it. So next we want to visit the neighbors of 1. You see the neighbors of 1 are 3. So let's go algorithmically. Next we have len q is greater than 0. Yes, of course it is greater than 0. We have 2 elements. We pop out the first element. We want to look into the adjacent elements of the first element, which is 1. So the adjacent elements of first element is of 1 are 0 and 3. 0 is already visited, so we will not go into this if. But 3 is not visited, so we will enter the if and we will append that to the queue, and we'll also mark it as visited. Alright, so next we add 1 to the CC. Then we have 2. We pop out 2. We see which elements are in the neighborhood in the adjacency of 2. We see 4, 0 and 3 are in the adjacency of 2, but for 0 and 3 they are already visited, so only 4 is not visited, so we add 4 to the waiting list and we also mark it as visited. So once that is done, we add 2 to the CC, then we go again, we pop out 3, and then we see, then we look in the adjacency of 3. In this case we have 2 and 1, both are visited, so we do nothing. So we append 3 to the adjacency to the connected components list. Then we have the last element that is left, 4, like in the queue. So we add 4. So we pop out 4, and we have and we look into the neighbors of 4. We see 5. So we add 5 to the waiting list, and the other neighbor is 2. So for that we don't trigger the this if statement, and also 5 is marked as visited, and then 4 is added to the CC. Then we have 5, and 5 is popped out from the queue, and in 5's neighbor list, in 5's adjacency list we have 4, but 4 is already visited, so we don't enter this if statement, and then we add 5 to the connected components, so we get 1, 2, 3, 4, 5. So now I think it should be pretty clear, right? Is there still any doubt?
Thank you.
All right. Okay, so that was BFS. There is one more algorithm that we have to talk about today, and that is DFS. So let's discuss DFS now. All right. Let's discuss it over here. Or maybe let's discuss it over here. If we already have the graph. So we okay. I will erase these and this. Alright. So now we want to talk about DFS. Even DFS can serve the same purpose that BFS does for finding the connected components. So if we run the BFS algorithm and we run a DFS algorithm, we will get the same connected component. The only difference will be that the order of elements that we search in BFS is different from the order of elements that we encounter in DFS. So let's look at how DFS works. DFS stands for depth first search. So what does that mean? For DFS, we start at let's have the seed vertex to be 0. Then we look at its neighbor vertex. We find 1. Now instead of looking at the other neighbor vertices of 0, we start looking at the neighbor vertices of 1. So we started off with 0. We look at the first neighbor vertex, first adjacent vertex, we find 1. Now we put 0 on hold and we start looking at the adjacent vertices of 1. So in adjacent vertices of 1 we find 2, 0 we have put on hold. So now we put 1 on hold We start looking in the adjacent vertices of 2. So in the adjacent vertices of 2, we have 3. So now we put 2 on hold. So, and we start looking at the adjacent vertices of 3. In the adjacent vertices of 3, we have 4. So we put 3 on hold and we look at the adjacent vertices of 4. There is no adjacent vertex to 4 except 3, which is already on hold. So there we terminate. And now we look at the other adjacent vertices of 3. So there is no other adjacent vertices of 3 that is not already on hold. So then we terminate this as well. Now we go one step back again. So we have for 2 we have another neighbor that we need to consider, that is 5. So now we abandon 2 and now we look at the adjacent vertices of 5. For the adjacent vertices of 5 we have only 2, which is already on hold. So here we terminate this and we take one step back. Now for 2 there is, like, we have already came back from 3, we have already came back from 5. So now there's nowhere new to go from 2. So we terminate it here and we move one step back. So moving one step back, we reach 1. There is no, so 1 had only 0 and 2 as adjacent vertices. We already explored 2, 0 is already on hold. So there's nothing more to do here. We terminate here and move one step back. And for 0, we have 1, 2 and 3 as neighbors. We already checked here, we already checked 2, we already checked 1. There's nothing new to do here, so we terminate it over here. And in this way we can traverse the entire connected component using Dfss. Is there any doubt in the explanation of Dfss? What we basically are doing here is that as soon as we find an adjacent vertex, we abandon the current vertex, put it on hold, and move to the newly found vertex and start exploring its neighbors. And as soon as we find a neighbor, we put that vertex on hold and move to the new vertex and start exploring the neighbor for that vertex. That is how DFS works. So the difference between BFS and DFS, breadth first search and depth first search, would be that in breadth first search, we first explore all the neighbors of the current vertex and then move on to exploring the neighbors individually. But in depth first search, as soon as we find a neighbor, we abandon the current vertex and start exploring the neighbor. So that is the difference between these two methods. If there is any doubt, then please do ask. Okay, so since there is no doubt, let's move on to the implementation of depth first search. How do we implement it? So in order to implement depth first search, let me clear this area a bit. Alright. So in order to implement depth first search, what we do is, instead of maintaining a queue as waiting list, we don't use a queue in depth first search. Instead, we use a stack. So if you are familiar with the concept of stack, you can immediately see why a stack would be a good fit for this use case, because we are putting things on hold and coming back to them later on. So the things we visit first are not the things which so we come back to them later on. So they need to be pushed to a stack, and then uh, they need to be referred to later on. That is something stack is really good at. So for people who don't know what a stack is just a list wherein things that come first get out the last. So a visualization that is usually implied with stack is uh, think of a pile of plates. Think of a pile of plates. So if you were to remove the plates one by one, then the plate that came on the pile last will be removed first. The plate that came on the pile second last will be removed the second, like will be removed second. So that is what stacks, like that is how you can visualize stacks. So basically, if you have 0, 1, 2, 4, and you input them and you push them to a stack, and then you start popping the elements, then 4 will go first, then 2, then 1, then 0. Something like that. So how can we use a stack? How can we use a stack to implement DFS? So we can use a stack in this way. So we have our first element as 0. We push that to the stack. Now we start looking at its neighbors. We have 1, 2. So we have 1, 2, and 3. So we'll just um, yeah, give me one sec. Right. So we first push 0 to the stack, and we start exploring its neighbors. Uh, yeah, sorry. First we have 0 in the stack. We pop 0 from the stack, and we start exploring its neighbors. We in the neighbors of 0 we have 1, 2, and 3. So we push 1, 2, and 3 to the stack. 1, 2, and 3. Right. Then since we so we push 1, 2, and 3 to the stack. Now we pop from the stack. We pop 3 from the stack. So we now visit 3. For 3, now we'll visit all the neighbors that 3 has. So we'll have 4, and so once we pop from the stack, 3 will go away, and then we'll insert the neighbors of 3, which are 2 and 4. So since 2 is already in the stack, it doesn't matter, we'll insert that anyway. Yep, so we'll insert that anyway, and then so we already visited 0 and 3. So now we have 2, we have 1, 2, 2, and 4. So we have 2 twice, but that doesn't matter. So in case of so the way we are implementing DFS right now, duplications won't matter. So we have 2 and 4 in the stack. So since 4 is at the top, we pop 4, and we see that 4 has no neighbors that we can traverse to. So we mark it as visited, and then we pop the next element that is available to us, that is 2. So we pop 2, and we see that we have 1 and we have 5 as the neighbors. So we push them to the stack, and we mark this as visited. Now we have 5 as the top of the stack. So we pop 5. We have popped 5, and we see that there are no available neighbors that we can visit. So we mark it as visited, and then we pop the next element from the stack, which is 1. So once we pop 1, we see that there are no elements to be visited. So we mark this as visited, and we move to the next one. So the next one is 2, which has already been visited. So we'll just pop it and move forward. And the next one is 1, which has already been visited. So we'll just pop it and move forward. So in this way, we visit all the connected components of of connect all the components that are connected to 0. Right. So uh, yep, that is how we implement DFS. If there is no doubt in that, then we can probably move on to the implementation and to the Jupyter implementation.
I just have a basic question. Like, what is the difference between these two things? I feel that breadth first search is better than this, right? Because depth first will be using a lot of resources in the memory and also iterations, right? Using when it is popping at the last 1 and 2.
Oh, you mean depth first? Depth first search is worse than breadth first search.
Like, how is that useful over breadth first search?
I'm not sure which one are you talking about to be more useful.
I'm saying that breadth first is useful than depth first, right?
Okay.
Because depth first will be using a lot of resources in the memory, for example, duplicating of that nodes.
Right. So there are certain scenarios in which depth first search will be more useful than breadth first search. So for example, if you're just filling up, like if you're just implementing like a fill bucket tool for paint, and in that case breadth first search will definitely be more efficient, I think. But like there are certain algorithms which require you to use depth first search for it to be more efficient, um, rather than breadth first search. So
Okay.
yeah.
Can you give an example wherein depth first search is better than breadth first search?
Yes. Right. So let's say there is a graph. So this is not related to image processing directly, but like shortest path. Yes. So something like shortest path, or let's say if you want to find, if you have a graph and you want to find whether there is a cycle present inside the graph, then in that case depth first search will be better than breadth first search. So something like that.
Yeah, makes sense. Yeah.
All right. So shortest path between two nodes. Yep, that could be. Uh, hmm, that could make sense. Or like you should try. Like you guys should try actually. You take an image with take a binary image and uh, like take a binary image of a maze and see and run breadth first search and depth first search and see which one reaches the from start to destination in lower number of steps. So you could try that exercise and find out something like that. So I think this is worth exploring. All right. So yeah, let's move on to the Jupyter implementation, the Python implementation of DFS. So,
Hello.
hello.
Sorry to interrupt, but you just gave the fill tool example for breadth first search, right? So I had this. I thought of this weird tool in Paint that if you give it 2 points, it just connects the 2 points with some weird curve.
Right.
It has some star-like shape. So does this one use depth first search?
I hmm. I think it uses some kind of a like it uses some kind of a shortest path algorithm, which is uh, I'm not sure actually. So is this the tool that you're talking about? Circle engine. Is this the tool that you're talking about? So let's say if I want to join from here to here, it creates a jagged line like that.
Yeah, something like that.
So I think this is somewhat of a shortest path algorithm, and it like tries to find the path that minimizes the energy um, of this path. So it probably finds like edge, the edge image of this like of this color image, and from that edge image, it so I'm just guessing how it has been implemented. So in that edge image, the edges have lesser weight, like lesser penalty, and the non-edges pixels will have more penalty of um, uh, like if the path goes through the non-edge pixels, it gets a higher penalty. So I think that is how they are implementing this. So this from point A to point B, they are basically the path basically wants to follow the edges, is what is how they have.
So the algorithm is much more complicated than any of the searches that we just learned, right?
Sorry, could you repeat that?
The algorithm is much complicated than the searches that we just learned.
Yep.
It's okay.
So if you want to look into pathfinding, you can look into Dijkstra and A star algorithms if you have heard about them. So I'll just write those down in the chat. Yeah, so you can look at these two algorithms if you want to look more into pathfinding. Okay, so let's move on to the implementation of DFS now. So we want to define a function for DFS which takes in a seed, and it gives us uh, a connected component. So right, and in between this we'll have to write some search code. So like we had a queue in BFS, we will have a stack in DFS, and the stack will be initialized with the seed. Like we had visited in BFS, we'll have visited in DFS as well. False into n, and we will have CC as well. So this is pretty much very similar to BFS, and we'll start the while loop while the stack still has elements. Keep iterating. What do we iterate? We pop out the first element of the stack. We pop out the last element of the top element of the stack, which we can access with -1. So -1 just means the last element of the list. So that gives you the top element of the stack, and we then do a stack dot remove cur. So this basically removes the top element from the stack. Now if the element that we just popped from the stack has already been visited, if not visited, so if it has already been visited, then we don't need to do anything. But if it has not been visited, if not visited cur, So if the current element has not been visited, then first we need to add it to the connected components, and we need to mark it visited char equals to true, and then we need to look into all the adjacent vertices of the current element in adjacency list of current, and if those are not visited as well, then we will add them to the stack. So we'll look into the adjacency list of the current element, and if the adjacent vertices of the current element are not visited, then we'll add them to the stack. Stack dot append. Alright, so that's pretty much it for the DFS code. So if I run this DFS, let's seed it to 0, and it should give a similar result to the BFS except for the order, and we get a similar result from BFS. We get 0 to 5, and if we seed it at 2, we should get a similar result, and we get a similar result. If we seed it at 6, we get 6, 8, 7. So we see that our DFS code is back. So is there any question regarding the DFS code? Is there no question? So yeah, like if there is no question, then that's basically it for today's workshop. So today we had to cover Hufflines transform, Huff circles transform, and graph traversal. We had to cover breadth first search and depth first search, so that we have already covered. Swaroop says that he has a different doubt. Where do I get the image folder you are using, and where should I keep them? Any directory where the notebook is there? Achha. Okay. So I was thinking, since the next session, the last session of image processing workshop, is a hands-on workshop and you will have to code. So I was thinking that we could spend some time, since we have 1 hour of workshop left. I was thinking we could spend some time setting up the environment in people who don't have it set up already, or who are having problems setting up the environment. So I'll stop the workshop recording now, and we can go ahead and look at some of the problems that you are facing setting up the environment. Is that, like, would you guys like to do that, or would you like to solve it in the break on your own? Like, I will be available if you need some help.